Hello, my name is Steve Miller and I'm the Technical Marketing Manager for the Simscape product family at MathWorks. In this presentation, we're going to see how we can use Simscape Driveline to simulate vehicle powertrains. Here are the key points I'd like you to remember about Simscape Driveline. First, it provides libraries of components for vehicle powertrain modeling. Those models can be used to design control algorithms, detect integration issues, and optimize your overall design. Simscape Driveline component models can be customized to meet your needs. You can enable and disable physical effects such as friction and backlash, and you can add losses and include temperature effects. Finally, Simscape Driveline models can be used for system-level analysis and to test embedded software. You can, for example, use it to estimate fuel economy, and you can convert the models to C code for hardware-in-the-loop testing. Here's the agenda for our presentation. First, we'll take a look at a couple of example applications where Simscape Driveline can be used. We will then build up a model from Simscape Driveline components, adjust the level of fidelity, and customize a component with Simscape language. Finally, we'll see how Simscape Driveline enables simulation-based workflows, such as automatic testing and report generation, and real-time simulation. Simscape Driveline can be used to model a dual-clutch transmission. In a dual-clutch transmission, the engine is connected to the transmission via two concentric shafts and two clutches. Dog clutches are used to pre-select the next gear to which the transmission will shift. When the transmission is in first gear, this dog clutch will slide over to the right. Power will flow from the engine through the green clutch to the green shaft, through first gear to the dog clutch connected to the secondary shaft, and then out of the transmission. When the transmission is preparing to shift to second gear, this dog clutch will slide over to the left, engaging second gear. But because the red clutch is disengaged, no power will flow through this connection. When it's time to change gears, the green clutch will disengage, the red clutch will engage, and power will flow through the red shaft, through the second gear to the secondary shaft, and out of the transmission. Simscape Driveline is used to optimize the design of the transmission, including selecting gear ratios and determining the shift schedule. It's also used to design and test the controller, including coming up with the shifting logic and the pressure control for the clutches. I will now shift over to the model so you can see what this looks like. Here is our model of the dual clutch transmission. If we go into this subsystem, we can see the two Simscape Driveline blocks that model the clutches. They are connected to two concentric shafts, or connected in parallel. These blocks represent the inertia of those shafts. These mechanical connections are connected to the subsystem where the gears and the dog clutches are modeled. The gears, via the dog clutches, connect to the secondary shafts, which then connects to the rest of the vehicle drivetrain. The control signals for the clutches come in via this bus. If we go back up to the top level, we can go into the transmission controller and see that the control of the clutches and the dog clutches is handled by this state flow chart. This chart is a state machine that controls when the gears engage and disengage. If we run the simulation, we can see in the animation on the state flow chart how the gears are changing. Here we can see the engine speed, so seeing the effect of those gear changes, and we can see that in our wide open throttle test we are up to 6th gear, and as we slow down we will go back down through the other gears, again the clutches engaging and disengaging. If we go back up to the top level, we can see how this model is used. We can use it to estimate the fuel economy. This estimates the fuel economy for the simple test we just performed. We can also use it to tune the shift schedule. Here is a MATLAB plot of the gear shifting schedule when the transmission will change to different gears. These parameters are all saved inside the controller. We could use this model to tune this gear shifting schedule in order to optimize fuel economy. Simscape Driveline can be used to develop hybrid electric vehicles. You can model an entire hybrid powertrain, including the mechanical drivetrain, combustion engine, electrical motor and generator, connected to a battery and a power converter. The model of the hybrid powertrain in Simscape Driveline can be used to test for integration issues, design the control system, and optimize system-level performance. I'll switch over to the model so you can see what this looks like. Here is our model of a hybrid electric vehicle. The vehicle dynamics are modeled in Simscape Driveline. You can see that the drive shaft connects through the differential to the tires and the model of the longitudinal vehicle dynamics. Going back up a level, we can see the power split device modeled in Simscape Driveline, where we have meshing losses, viscous losses, and other effects. This connects to the electrical system. The electrical system includes a motor and a generator. The motor is modeled using Simscape electronics and connects using these mechanical connections to the rest of the powertrain. We also have a DC-DC converter and a battery. The control system is modeled here. We have mode logic modeled in stateflow to control the transitions of the modes. We have an engine speed controller, motor and generator controllers, and a battery charge controller. When we run the simulation, we can see how all of these different systems integrate together. Here you can see a plot of the vehicle speed as we go through a standard drive cycle, the voltage on the DC bus, the battery, and the temperature of the DC-DC converter. This model integrates all of these different subsystems, allowing us to detect integration issues in simulation and optimize vehicle performance. We can also measure fuel economy, another measure of vehicle performance. This summarizes 2 example applications for Simscape Driveline and some of the tasks where the models are used. Now that we have seen a few example applications where Simscape Driveline is used, we will build up a model of a simple vehicle powertrain. In this demonstration, we're going to see how we can use Simscape Driveline to model a vehicle powertrain. Our model will include an engine, torque converter, gear, differential, and tire dynamics. We would like to use this model for controls development. We will develop it in Simscape Driveline so that we can use it within the Simulink environment. This is what the model will look like that we will build, and this is what the simulation results will look like for a 10-second test. I'll now switch over to the model so you can see how this is done. To get started, we'll enter the command sscnew into the MATLAB command window. This will open up a new Simulink model with the settings recommended for Simscape models. The first thing that we'll need is an engine model. We'll click in the diagram and type engine and select from the engine models available. Double-clicking on the block will expose the parameters that we can adjust in the model, including the model for the fuel consumption and the speed controller. We will specify the inertia and the initial velocity. Here we can specify the units and the parameter value, and these can be MATLAB variables so that we can vary them automatically. The generic engine block has 2 mechanical connections. This represents the connection to the vehicle body. We'll create a rigid attachment by using a mechanical rotational reference. This signal is our throttle input. We'll specify a constant throttle of 0.5 or 50% throttle for our test. Simscape and Simscape Driveline use solver technology above and beyond what is available in normal Simulink. To have access to those settings, we'll attach the solver configuration block. This mechanical connection goes to the rest of the drivetrain. The first component in our drivetrain is the torque converter. We'll attach that here. Next, we'll attach an inertia that represents the inertia of the remainder of the drivetrain. We'll type in inertia, and here if we go into the block we can specify the inertia value, the units, and specify if this should be a runtime parameter, or a parameter we can tune in simulations involving C code, such as hardware in the loop testing. The next component in our drivetrain would be the transmission. To keep things simple, we'll just use a single gear. And we'll set the output of the gear to rotate in the same direction as the input shaft so that the vehicle moves forward. The next component in our powertrain is the differential. From here, we'll connect to the tire models. I'll type tire to select from the tire models that are available, and copy and paste for the left and right wheels. We'll connect the tire models to a model of the longitudinal vehicle dynamics. And so that we can see the output of our simulation on a Simulink scope, we'll connect a converter block and a scope. The converter block is where we can specify the units. So we'll set them to be kilometers per hour. At this point, our simulation is complete. We can run the simulation and view the results on a Simulink scope. Another way to view the results is to right-click on the block and select View Simulation Data. This will open the Simscape Results Explorer, and here I can see the speed of the vehicle. Here you can see it goes to about 22 meters per second, or we can set it to miles per hour. We can also look at the results of all of the other components in the network, including the amount of fuel consumed by the engine and the power produced by the engine. In this demonstration, we have seen how we can model a simple powertrain and evaluate the simulation results using Simscape. In this demonstration, we're going to see how we can model a transmission and a transmission controller in a Simscape Driveline model. We have a model of a vehicle with a very simple transmission. We would like to add a 4-speed transmission and a transmission controller to that model. We will do it using Simscape Driveline to model the transmission and Stateflow to model the transmission controller. The transmission will look like this with planetary gears and clutches, and our transmission controller will be a state machine. When we run the simulation, we will see how the vehicle performs on 2 different tests. I'll now switch over to the model so you can see how this is done. Here is our simple model of a vehicle powertrain. We have an engine, torque converter, a single-speed transmission, and longitudinal vehicle dynamics connected to tire models and a differential. We would like to replace this single-speed transmission with a 4-speed transmission and a controller. We have prepared this transmission in advance. So we will remove the single-speed transmission, come over to our set of blocks, and drag in our 4-speed transmission along with the controller. We will connect the mechanical connections, and then also connect the speed of the vehicle to our transmission controller. Let's take a look at the transmission. Our transmission has been modeled using Simscape Driveline blocks. We have planetary gears and clutches that model the transmission. The gear ratio between the input shaft and the output shaft is controlled by which of these clutches are closed. This clutch schedule shows which clutches need to be closed to select the different gear ratios. For example, to be in first gear, clutches A and D must be closed, and this is the ratio that will result. To control whether or not these clutches are open or closed, we have a set of clutch pressures that come in through this signal. To control those, we have a state machine that governs which of the clutches are closed. In first gear, clutches A and D are closed, just as we saw in the clutch schedule. The transitions between the clutches are done at different vehicle speeds. If we run the simulation, we can see how our transmission and transmission controller behave. Here we can see that the vehicle accelerates, going through the different gears, until 30 seconds. At 30 seconds, it encounters a hill, and we can see that the vehicle slows down. If we go back to the Stateflow model and rerun the simulation, we can see an animation of the state chart. So it starts in first gear, and it goes all the way to fourth gear. Now let's see how our transmission behaves with a different drive cycle. We are going to cut the throttle after 40 seconds and see how the vehicle behaves. We will bring open the state chart and have our plot here and rerun the simulation. Here we can see that the vehicle accelerates to 30 seconds as before, encounters the hill and slows down, and then after we cut the throttle, the vehicle slows down even more, and it finished the simulation in third gear. In this demonstration, we have seen how we can model a 4-speed transmission in Simscape Driveline and add a controller using Stateflow. There are a wide range of components available in Simscape Driveline for your powertrain modeling needs, and you can adjust the fidelity of those components to match the level of detail you need for your engineering task. There is a mean value engine model that produces torque averaged over a piston cycle. You can use this model to size engines and to include throttle transients. There is also a crank angle resolved model where the torque varies during the piston cycle. You can use this to excite vibrations in the drivetrain. For shafts, you can model shafts as an ideal rigid shaft. You can have shafts whose inertia varies with the rotation angle, and you can have flexible shafts that have torsional flexibility. The gear libraries have a wide range of components. Each of them contains loss models. These loss models are valid for all shaft speeds and loads, including planetary gears where the loading can affect the efficiency. You can also include temperature effects with your gear models. This includes the heat produced and transferred to and from the gear, and modify the behavior of the gear based on its temperature. You can also include nonlinearities into your model, including backlash, friction, and gears that are not back-drivable or self-locking gears. There are a wide range of clutch models available in Simscape Driveline. These include friction clutches, such as a cone clutch. The parameterization options allow you to customize the friction model. There are also positive contact clutches, such as dog clutches and synchronizers. You can parameterize these to include backlash or use a friction approximation that is appropriate for hardware-in-the-loop testing. And there are fluid coupling models, which are valid at all speeds and shaft loads, such as a torque converter. You can parameterize the transmission lag such that it is applicable for the test you wish to run. Simscape Driveline also provides tire models. They are with and without slip, and there are various options for the friction coefficients, including friction coefficients that vary based on an input signal. You can adjust the effects in your tire models, such as adding or neglecting compliance, and adding and neglecting rolling resistance. Finally, if you wish to create your own custom tire model, we provide a set of components that you can use to assemble a tire model that meets your exact requirements. Within Simscape Driveline, there are a wide range of components, and you can adjust the fidelity to exactly meet the needs of your simulation. In this demonstration, we're going to see how we can model a four-wheel drive vehicle with limited slip differentials using Simscape Driveline. We have a model of a four-wheel drive vehicle. We would like to evaluate the performance of the drivetrain with different types of differentials. In order to test this system, we'll need to vary the surface conditions at each wheel. We will run a transition test where the vehicle starts on ice, and then as it moves forward, it moves onto a high friction surface. In this scenario, the center differential will have the largest effect on the drivetrain behavior. We will also run a split test where two of the wheels are on ice and the other two are on a high friction surface. In this test, the front and rear differentials will have the largest effect on the drivetrain performance. We will compare the behavior of the drivetrain with the two different types of differentials using Simscape Driveline. We will see a model of a limited slip differential, and we will see how we can vary the coefficient of friction at the wheels based on the vehicle position. And we will see that the limited slip differentials will allow the vehicle to accelerate much faster than the open differentials. Here is our model of the four-wheel drive vehicle. We have the longitudinal vehicle dynamics, tire models, front and rear differential, and the center differential. We can vary the types of differentials using variant subsystems. Let's look at the front differential. We have two different variants. One is an open differential and the other is a torsion differential. The open differential is modeled simply using the differential block from Simscape Driveline. If we enable the torsion variant, we can see how we have assembled this component. It is assembled using the gear blocks in Simscape Driveline. Because the Sun Planet worm gears are not back drivable, this configuration results in a torsion differential. In the center differential, we have four different variants. The viscous variant is simply a nonlinear damper. The open shaft has no connection to transmit torque. The rigid shaft is used as a torsional spring damper. And the lockup variant, which I will enable, has been assembled from a few Simscape Driveline components. A clutch pack will be engaged if the shaft is transmitting torque. To test this system, we will need to vary the road conditions. Looking at the tires, we can see that the coefficient of friction is fed in as a Simulink signal. We determine the coefficient of friction based on the position of the vehicle. Our subsystem can test the vehicle under two different road conditions. One is a transition, where we go from a low friction surface to a high friction surface, and the other is a split, where two of the wheels are on a low friction surface and two are on a high friction surface. For our first test, we will use the transition road condition. In the transition road test, the center differential has the largest effect on the behavior of the drivetrain. So we will test all four different center differentials on these road conditions. At the conclusion of these tests, we'll create a MATLAB plot that shows the behavior of the vehicle. Here you can see the MATLAB plot. The open differential had the worst acceleration. It took the longest for it to get off of the ice and onto the high friction surface. The rigid shaft had the best behavior. We can see that the viscous and the lockup differentials were somewhere in between. If we plot the speeds of the tires in the vehicle, we can see how the system performed. This is for the rigid shaft case, the last one. We can see that all four of the wheels were slipping. As the front wheels reached the high friction surface, the vehicle started to accelerate faster, and we can see that the wheels started to slip less and less. If we were to run the same test with the viscous differential and replot the speeds of the tires, we could see slightly different behavior, where some of the torque is transmitted to the rear wheels even as it's still on the ice, and it takes a bit longer for the vehicle to accelerate. Now let's do the test with the front and rear differentials. For this, we will switch to the split road condition. We will run this test first with the open differential and then with the torsion differential. When we plot the vehicle speed, we can see that the open differential had worse acceleration than the torsion. In the case of the torsion differential, because it locks up, the vehicle can accelerate because the two wheels that are on the high friction surface are able to move the vehicle forward. In this demonstration, we have seen how we can model open and limited slip differentials and test it on various road conditions. Using the blocks from Simscape Driveline, you can create a very customized model. Further options for customizing your model are available using Simscape language. In this demonstration, we will see how we can model a custom engine mount using Simscape language. We have a model of a vehicle powertrain. Instead of assuming that the engine is rigidly mounted to the frame of the vehicle, we would like to include a spring damper which has a nonlinear stiffness. To create this component, we will use Simscape language. For our engine mount, we have a custom equation. We will implement that equation in Simscape language. The Simscape language is MATLAB based, it's object oriented to improve reuse, and you can use it to define implicit equations, which include DAEs and ODEs. I will now switch over to the model so you can see what this looks like. Here is our model of a vehicle powertrain. We have an engine, torque converter, 4-speed transmission with clutches and planetary gears, vehicle dynamics including tire models and a differential, and a transmission controller implemented in Stateflow. We would like to include the effects of an engine mount into our simulation. I will run the simulation, and then we will review the simulation results. Here we can see how the vehicle performed, and if I right-click on the engine mount, we can review the simulation results. Here in the Simscape Results Explorer, we have selected the custom engine mount. We can see the amount of torque that the engine mount experienced, its amount of deflection, and the speed of deflection. If we go back to the block itself, we can take a look at the source code. This block was implemented using Simscape language, which is based on MATLAB. Here we can see our custom equation and the parameters that we let the user change when they want to modify how it behaves. In order to go through this code in more detail, I will switch back to PowerPoint. Here is the Simscape language code that defines our custom component. Our custom engine mount needs to have two mechanical connections. Those are defined here. We reuse the domain definition from Simscape so that our block is completely compatible with all the libraries that are provided. The next thing we need to define is the user interface. These are the parameters that we wish to allow users to adjust. This is specified here. We specify the default value, the default units, and the prompt that the user sees. We simply define the code and the user interface is created automatically. In the next section, we leverage MATLAB. Here we use MATLAB code to verify that a parameter value is legitimate. In this section, you can use MATLAB functions and expressions to do typical tasks, such as analyzing parameters and performing preliminary computations. In the next section, we define how the component behaves. Here are the equations that define how we expect our custom engine mount to behave. Those equations are defined here. We can define equations based on variables, their time derivatives, parameters, and other quantities. A key difference between this code and MATLAB code that you may be used to is that here we are defining simultaneous equations. These are implicit equations. They are part of the entire network where the equations will all be solved simultaneously. We can define DAEs and ODEs, and important to note is that assignment is not required. It isn't as if we know what omega is and we are calculating t. All of these equations will be solved at the same time. We are not specifying inputs and outputs. It's a full implicit set of equations. In this demonstration, we have seen how we can define a custom component. Now that we have seen how to build and customize Simscape Driveline models, we will see how Simscape Driveline enables simulation-based workflows. In this demonstration, we're going to show how you can automatically run tests on your vehicle powertrain and document the results. Developing a vehicle powertrain can involve iteration, where you come up with a design change, test that change, evaluate the results of those tests, and come up with a new change. The step where you run the test and evaluate the results can require a lot of time. We would like to accelerate that step. We will show how you can use Simulink Report Generator to automatically document those tests and the results. We will use a model of a dual clutch transmission. Using Simulink Report Generator, we will automatically run those tests and include plots, screenshots of the model, pieces of code and other valuable pieces of information into a document. I will now switch over to the model so you can see how this is done. Here is an example of a report produced by the Simulink report generator. We automatically generated this report as we were testing our vehicle powertrain. Here you can see some MATLAB code, screenshots from the Simscape Driveline model, screenshots of the stateflow model that controls the changing of the gears, plots from the scopes, and a table summarizing the results. I'll show you how we automatically generated this report. Here's the model that we're working with. It is a dual clutch transmission that has clutches and gears in order to implement the transmission, vehicle dynamics, and a transmission controller. The Simulink report generator interface looks like this. You graphically assemble the structure of your report by dragging and dropping elements into it. When you're finished configuring the report, you can simply run it. It will automatically execute any of the MATLAB code you've entered, and we use that MATLAB code to set up our tests. We are going to run cycles 6 and 7, and we will generate report short 1. So I'll click on the lightning bolt, and we will get started. So the first test is being run, and we can see that we are running drive cycle 6, which is a simple wide open throttle test. At the conclusion of the test, the report generator will take screenshots of the scopes and portions of the model if necessary, and then it will set up test 2. In test 2, we are running drive cycle number 7. So you can see it is transitioning through different gears as it follows a velocity profile. At the conclusion of the test, it takes more screenshots and then assembles the report. So this is short 1, the report that we just created. And you can see we have, again, MATLAB code, screenshots, and the simulation results all the way down at the bottom. Now that I've created this report, if I had new iterations on my design that I wanted to run through a certain set of tests and evaluate those results, I could simply modify the model, rerun this, and the results of those tests would automatically be documented in a report. That report can be shared with other people and can be created in various formats. Another important simulation task is hardware-in-the-loop testing, where you connect your model of the physical system to your embedded controller, hardware and software, to test how it behaves. With Simscape, you can use fixed-step implicit solvers locally on the Simscape networks. This allows you to use implicit solvers only where it is necessary. This reduces the amount of computation per time step and allows your simulation to run faster. The typical workflow is that you simulate your entire system with a variable step implicit solver to make sure that it is behaving the way you want it to and that your results are accurate. To run in a hardware-in-the-loop test, you need to configure it to run with a fixed-step solver. Common for simulation environments is to apply a single solver on the entire model. For the physical networks or the physical portions of your model, these may have very stiff equations and may require an implicit solver. With Simscape, we can use an implicit solver locally on each individual physical network. This allows us to use an explicit solver, one that requires fewer computations on the rest of the model. By configuring a solver per physical network, we can also run the different physical networks at different sample rates. So for example, an electrical network could be sampled at a higher rate and a mechanical one at a lower rate, reflecting the natural frequencies of each system. The primary use of this is to speed up simulations where fixed-step solvers are required, for example, hardware-in-the-loop testing, where you convert your model to C code and run it on real-time hardware. We will show you how to do this in the next demonstration. In this demonstration, we're going to show how you can configure a Powertrain model for hardware-in-the-loop testing with Simscape Driveline. We have a model of a vehicle powertrain. We are satisfied with the results we get from desktop simulation with a variable step solver. We now need to configure this model so that it can be used for hardware-in-the-loop testing. However, portions of our model are numerically stiff. We're going to need to use the Simscape local solver to make this model real-time capable, and so that we can test it with runtime parameters. Here are the steps that we'll go through. First, we will configure our model to use a fixed-step, fixed-cost solver appropriate for hardware-in-the-loop testing. We will then rerun the model with that solver to verify that we still get the same results from our reference test. Next, we will generate C code from the model. After we have created that C code, we will download it to the real-time hardware. We will rerun the simulation and verify that we get the same results we got on our desktop computer. Finally, we will do our test. We will vary a parameter in the Simscape Driveline network and see how the control system reacts. I will now switch over to the model so you can see how this is done. Here is our model of a dual clutch transmission. When we go into this subsystem, you can see the two clutches that act in parallel to control the changing of the gears. These are connected via two mechanical connections to the rest of the transmission, where we can see the gears, the dog clutches, including the reverse gear. These dog clutches are used to pre-select the next gear to which the transmission will change. This is connected to our model of the longitudinal vehicle dynamics, where we have the final drive ratio, inertia, and aerodynamic drag. These systems are connected to our control system, where we have a state machine that controls the selection of the gears. When we run this simulation, you can see how it performs on a full throttle test. This scope shows the speed of the vehicle as we accelerate for 15 seconds. We also have a plot of the engine speed. Here you can see the transmission is changing gears. We are happy with how this model performs on desktop simulation. We would now like to configure this model for real-time testing. To do that, we'll use this MATLAB script to walk through the steps. The first step is to generate a set of reference results using a variable step solver on the desktop. We are using solver ODE23T, so we will rerun the simulation, and at the conclusion of the simulation we will save these results onto a MATLAB plot. So here is our MATLAB plot showing the reference results. We will now use these commands to configure the simulation to use a fixed step, fixed cost solver. Here you can see that we are using global solver ODE1, and here you can see that we have enabled the Simscape local solver. So we are using the local solver, backward Euler integrator, with this step size, and we have used fixed cost simulation. This means we are limiting the amount of computation per time step, which will help us avoid overruns on the real-time system. We will take these results and add them to the plot. And when we look closely, we can see that the simulation results match quite well. So we can see that we have selected real-time settings that allow us to have accurate results, and we can tell that it runs quite quickly. Now we will figure out which parameters we would like to tune on the real-time system. Using these MATLAB commands, we will switch to the inertia, and this represents the inertia of the vehicle. So we are going to set this to be a runtime parameter, meaning that we can change its value on the real-time hardware without regenerating the C code. This will accelerate tests such as hardware in the loop testing, where we will be running this model with the embedded hardware and software. We can modify the behavior of the physical system and verify how the control system reacts. So now that we have enabled our real-time runtime parameters, those that we wish to change on the real-time hardware, we will use Simulink Coder to convert this model to C code and download it to the real-time hardware. Here you can see the real-time hardware which we are using. It's running Simulink real-time, and it's connected to a monitor where we will be able to monitor the behavior of the simulation on the real-time target. We'll also be running in external mode, so we'll be able to see the simulation results on a Simulink scope. Switching over to the MATLAB window, we can see all of the messages that are being generated as the C code is produced. And now we can see the model is downloaded to the real-time target. We will switch to external mode so we can monitor the behavior of the simulation on the Simulink scope, connect to the target, and run the simulation. At the conclusion of this 15-second test, we'll upload the results. You can see both the vehicle speed and the speed of the engine on the two plots that are shown on the scope, and you can see those results being updated on the Simulink scopes as well. So we have reached the conclusion of our 15-second test on the real-time hardware. We will upload those results and add them to our plot, and we can see that the results on the real-time system exactly match what we had on the desktop. We also saw that we didn't have an overrun, which means our model is running fast enough. Now we're going to change that block parameter. We're going to change the inertia of the vehicle from 1600 kilograms to 1800 kilograms. And then we will rerun the simulation with this new configuration for our model of the physical system and see how the control system reacts. We're not using external mode, so you can monitor the results on the monitor that's connected to our real-time hardware. The simulation is now complete. We will upload those results and add them to our plot, and if we zoom out, we can see that the behavior has in fact changed. We can see that increasing the weight of the vehicle means that it accelerates more slowly, so it doesn't reach the same maximum speed at the end of 15 seconds. In this demonstration, we have shown how to configure Simscape Driveline models for hardware-in-the-loop testing. In this presentation, we have seen that Simscape Driveline provides libraries of components for vehicle powertrain modeling. You can use those to design control algorithms, detect integration issues, and optimize the design. Those component models can be customized for your own needs. You can enable and disable physical effects, add losses, include temperature effects, and create your own components using Simscape language. And finally, we have shown that you can use Simscape Driveline models for system-level analysis and to test embedded software. This concludes our presentation. We would like to take some time to answer your questions. Please enter your questions into the chat window. We will be back in a few minutes to answer them.